Okay, section 8.5. We have 3 theorems that we're going to be concerned with. So first of all, I want you to go ahead and read section 3.5, pages 351 through 54, and take some notes on those 3 theorems. Make sure you understand the theorems. We're going to look here in a minute at the proofs of the theorems, although the proof of the second and the third one is suggested to you. Actually, the third proof is given to you, the second one suggested to you, and they kind of just they wave their hands at the first one. So we'll look at the proofs and see what happens. But I want you to read first and then come back. Okay, so we've read section 8.5, and now we're ready to look at these theorems. The first theorem says that if I have any triangle whatsoever and I put in a segment that is parallel to one side of the triangle and intersects the other 2 sides of the triangle, I split up the 2 sides that intersect into some lengths, A and B and C and D, let's say. And our goal is to somehow show, according to the theorem, that A over B equals C over D. Now, from our means extremes proportion business, we also could form 3 other proportions here. C to A equals D to B, or A to C equals B to D, or B to A equals D to C. So let's just look at it now as this one going from the vertex of the triangle A to B equals C to D. Great. Do we see any similar triangles in this diagram? And the answer is yes, we do. We see the small triangle right here, similar to the entire large triangle. I'll let you think about that and justify that for a minute. Okay, and I hope saw that we've got some corresponding angles congruent and a reflexive angle congruent, so that's going to give us angle, and therefore our ratios of corresponding sides, small triangle to large triangle, would be A to A plus B equals C to C plus D. Now at that point, we say, well, those aren't quite the same thing, but maybe I can manipulate this proportion down here and turn it into that one. And let's see if we can do that. Okay, so we've got A to A plus B equals C to C plus D. What I'm going to do here is I could cross multiply and then reform a proportion. I also, and we'll look at that second, I also could reciprocate my relationship here, correct? I know I've got one proportion that works, so I know if I reciprocate, I get A plus B over A equals C plus D over C. I could then split that up as a fraction. A plus B over A is A over A plus B over A equals C over C plus D over C. Well, A over A and C over C both equal 1. I could cancel those out on each side, and that gives me B over A equals D over C. Head back up. Is that going to be what we're looking for the side splitter, what they call the side splitter theorem here? B to A equals D to C. Indeed, B to A equals D to C. We also could have cross-multiplied, as I said, the second way we could look at this. So if I do my means extremes product theorem on my initial proportion here, I've got AC plus AD equals AC plus BC. And you note we have an AC on each side, which will cancel, so I have an AD equals B times C. Then I can use my means extremes proportion theorem and go ahead and set up a proportion. And if I'm going to pick an A here, I need to have my D here, because my means extremes product theorem has to be A times D. And I could put the B either here, above here, or I could put my B over here. Looking at side splitter theorem, the way it's set up, I'm going to go ahead and put my B here, and therefore my C here. So then again, do we have side splitter? A to B, C to D, A to B equals C to D. Now there are other patterns that I can look at to keep track of the side splitter theorem. Clearly B to D equals A to C, or D to B equals C to A, or B to A equals D to C. As long as I've got one of those four proportions that I keep track of, then I can get the other three for free as I need them. So that's the side splitter theorem. On we go. Okay, the second theorem says there, if we've got a set of parallel lines, three or more, cut by some transversals, and I'll cut by a transversal here, and I'll cut by a transversal here. So as if those lines are parallel, we wind up getting ratios, we get proportions that the segments formed, A to B, will be proportional here, C to D, or B to A equals D to C. That's what we're looking for. Why would that be true? Well, the key is, and they showed you in the reading, is they said, look, if you were to draw in a segment to create two triangles here, and we'll draw that in here. Note then what you've got here with each triangle. With each triangle, you've got a side splitter in this triangle with these two segments here, and in this triangle, we've got a side splitter with those segments. So, let's call these segments R and S. I then know by the side splitter theorem with the left triangle here that A to B equals R to S. I also then would know that R to S equals C to D with the right triangle formed here. So if two things are equal to the same thing by the transitive property, those two things are congruent, so therefore A to B equals C to D. And again, in words, if three or more parallel lines are cut by a transversal, then those parallel lines divide the transversals proportionally. On we go. Okay, our third and final theorem, they give you the proof for it, so I'll let you look at that in your book. They're going to create basically a side splitter theorem by extending two sides of the triangle given, and then they set up a side splitter. What I want to make sure that we look at is here that our pattern. If you can keep track of the pattern for this theorem, it's going to be pretty straightforward. And it says that, the theorem says that if you take any angle in a triangle and bisect it, so let's say we bisect an angle in the triangle such that angle 1 is congruent to angle 2, the side to which that bisector is drawn is split up into two parts, x and y. And I have the two sides of the triangle to which I did not draw that bisector. And in this case, that would be, say, A and B. The theorem says that A over B equals x over y. Now, the way that I choose to keep track of that pattern is that as I look at the angle bisector, I pick one side and swing toward the other. So I've got A to B. And then if I go up to the side that that angle bisector splits up, I go in the same direction, x to y. So note that again. Here's my angle that's bisected. Start with one of the two sides. I go A to B. Go in the same direction on the side of the triangle that's been divided up by the bisector, and I go x to y. So that's how I choose to kind of keep track of this theorem, so I'll be able to remember it if I've got a problem where I need to use it. Looking for proportions where I've got a triangle where an angle's been bisected. So on to problem solving in class tomorrow. Hope this helped. Bye.